Hi, my name is Watson Williams, and today is April 12th, 2017. I'm here to talk a little bit more about my theory of time equilibrium, and I have some previous material on the subject. Here are the videos that I have already uploaded. As you can tell from the title of this video, it's episode 2. And what we want to do today is try and understand what the time field is about, what indication, what sort of things kind of indicate or suggest that a time field might be valid, and then we're going to look again at the example that I gave in episode 1 because I felt like I didn't go over it very clearly, so we're going to do that too. So when we think about relative lengths of time, or whenever we think about time conventionally in general, we just think of the timeline. And if you compared relative lengths of time, they would all be compared along an axis. But if time was two-dimensional, your lengths of time would be set up between an angle of 0 and pi over 2, because that's just the assumption of time equilibrium, is that lengths of time are equal. And then if they are equal, what does that mean here? For the observation that lengths of time are different, it's like a two-dimensional projection onto a one-dimensional, onto 1D. These are all supposed to be of equal length, but the perpendicular projection is where it lands on the primary axis. I hope that makes sense, because it's just, it's not meant to be overly complicated. This is about a holistic and integrated view of time. Equilibrium is a common concept in physics. It's very fundamental, really. And as I say, even the universe itself is moving towards a state of equilibrium, thermodynamic equilibrium, and it might just be anecdotal, but still, it's like, well, maybe we can find equilibrium in time. I mean, relative lengths of time are taken to be equal, but their projection, like if time is really two-dimensional, like part of what I'm saying is, or part of what's implied is that, you can't really access the second dimension of time, because it comes out as just time slowing down, but it's really going in a different direction. It just looks like it's stopped or slowed down. But we'll actually get into that in more detail in another episode. But because right now we just want to look at the fact that if we're imagining diverging from what we call the primary axis, Tx, the primary timeline, is, we haven't changed much, because all we're wanting to look at is what's happening between relative observers here. And but if it's the case that time is equal in both, like, you go out and then you come back whenever you come to rest again with the rest frame. But do you come out behind it at the same point, or even out in front of it? No, you wouldn't. You wouldn't expect to come out beyond that amount of time, because then you would be in the moving frame, but you would have somehow experienced more time. So like more time would have gone by. And if you come in behind, it's like, well, maybe it was like going to be an equal or less amount of time, maybe, if the distance from here to here was long enough. But it's already looking like, no matter what you do, like if you assume that there's another dimension of time and that the moving frame diverges off, it's already looking like it's going to be traveling farther through time. So you have to like somehow justify it with the projection, whether it's like that, or if you just assume that whenever you come to rest, you're actually merging again, like right back into the same moment as the rest frame, totally resynced. Then, since this arc is longer than this line, it implies that there's an extra. It just implies on the face that that from A to B is longer than it appears. And then also we have this clue that the derivative right at the top of the curve here, it implies that time was already going parallel with the primary axis before returning to rest, and that implies that it seems to imply some curvature also. And so then we came up with the gear partition, and then the +2 - 1, it's like, 1, 2, minus, +1, +1, -1. That gets you to from 0 to 1. Repeat the process and you'll get from 1 to 2, etc. And of course, this model of time is the same as the way that clocks run. And now we're coming back to our example, and we see that, alright, so what we want to say is that time is that you can do your free body diagram this way or this way. And if you do it this way, it's the classical way. This way is my method. And they're exactly the same triangle proportions, but the sides are different, and the angle, this theta here is the angle there, and beta is this beta here. And that's why whenever you take the cosine of this angle, you get VT over CT. The T's cancel, so that's your V over C. And of course, it's equal to the square root of 1 minus little t squared over big T squared. But it's also equal to, since it's the same angle here, and I allege that the sides are all the same length, but just different factors here, you can see that that V over C should also be equal to K times delta T over T plus delta T, which is equal to big T. And K is interesting because it's a factor that whenever whose behavior depends on delta T, and whenever delta T goes to 0, then K goes to infinity. But that's okay, because infinity times 0 is 0, and that just that's just whenever the hypotenuse collapses onto the base leg, and you just have two line segments laying flat over each other. And when K goes to infinity, when delta T goes to infinity, K goes to 1, which shows that delta t and k times delta t are getting closer to being the same length, which will become more relevant in just a minute if you wait. But yeah, so this, in our example, we have t is 75 minutes, little t is 60 minutes. That gives you v of 0.6 c, and k comes out to 3. Delta t is 15, which is 1/4 of 60 minutes, and 75 over 60 is 1.25. So whenever we go to do our chronon, our little time loop diagram, what you would do in this example is you would write out, since little t over big T is this, it's 4/5, like you get your reduced fraction, and in this case it comes out even, but in other cases obviously it might not come out even, and I'm gonna have to do a whole episode on just that. But here it's just important to see that it's a 4:5 ratio, so that's telling you that, like, at the fundamental scale, like the chronon scale, you're gonna have 5 rest loops for 4 dilated loops that are dilated again by a factor of 1.25, and here's all the relevant data there, and you can just see that both the straight line distance from here to there is the same. What, 5 loops times 1 is the same as 4 loops with a diameter of 1.25, and then whenever you use pi, 5 times pi over 2, which is a half arc length, and 4 times pi, 5/8, which is the new radius, that's half of 5/4, and then yeah, that's it. And so that's how you would interpret it. So it's like the same length of time, and then again we'll get into this in more detail later on, but if time is projected, then its maximum forward motion is at the top and bottom, and its minimum forward motion is at each intersection point here with the primary axis, and so it gives you like a pulsing of time. But here's the reverse Christmas Eve proof that shows that V over C is equal to this. Classically, we know that, but it's also equal to K times delta T over T plus delta T. And this shows it. And you can pause it and look at that if you need to. I don't really have time to go through all the details of the process with the rest of the time that I have. I have like 1 minute remaining, but yeah, you can just go back over that and see that it comes out with K. This term is your K, and then you'll have a delta T over big T in the bottom, or T plus delta T. Like I just switched that out there at the very end. But the logic of it is that if our assumption that a second dimension of time exists is consistent with the classical setup, then the assumption is plausible. The assumption is consistent, as this shows, or seems to show. Therefore, the assumption is plausible. And yeah, that's my assumption, or that's my best attempt at a modus ponens, that I'm going to have to make a continuation on this.